Hello, everyone. My name is Harrison, and just a quick introduction, since we're moving in a different direction. I'm a current rising sophomore here at Yale, and I'm thinking of studying either physics or astrophysics. And over the summer, I had the pleasure to be under Professor David Moore and grad student Yuhan to develop an FPGA-based feedback for just cooling the center of mass motion of these levitated nanospheres. And to just start off with a brief little introduction on the idea of levitation, some levitated objects. Oh, okay. Some ideas of levitated objects in everyday life. I remember the first day I ever walked into Professor Moore's lab, I saw this globe that was hovering, that was just spinning around of the planet. I thought that was just so cool. And that's usually used using magnets. And a bigger idea in East Asian countries, there's these trains are also magnetically levitating, moving at very, very high speeds, carrying lots of passengers. However, in our lab, we're working on optically levitating, so we're using lasers to trap these nanoparticles in a vacuum. And this was an image that Yuhan gave me, where you would have some sort of nanoparticle in here that's just levitating in space. And what makes these two different is that a train's pretty big. So that's around maybe 300 meters, whereas this is maybe like 100 nanometers. So throughout this presentation, I wanted to discuss the idea of these field programmable gate arrays, these FPGAs, as well as how we can use those to develop a real-time quantum control to slow down nanospheres in these spaces. And to just start off with a little bit of motivation on like the why we are doing this. So the reason why we want to slow down these nanospheres that are trapped, that are optically levitating, is because we can search for physics beyond the standard model. I know like most of you guys' presentations before this was talking about standard model. If there's anything else out there that we could find, this experiment would help us out. Also developing better impulse sensors, just motion and that kind of stuff. Also just testing these fundamental laws at microscales, since this experiments at a very, very small scale, if we can test fundamental laws such as like the Coulomb's law or Newton's gravitational law at very, very, very small scales, it could tell us more about how these laws work. Also just quantum mechanical states for these macroscopic particles. Since as we slow down these particles, it would behave more like a quantum particle, and then we can find the transition between the classical state and the quantum state, as well as other astrophysical experiments, like LIGO and that kind of stuff, looking for gravitational waves, dark matter. And if you want to know more, ask Professor Moore, because I'm not very good at physics yet. And this is a diagram that Yuhan gave me, where you might have some sort of hypothesized dark matter particle that would influence the motion of this nanosphere. And to just show the experimental design, what we want to do is we have some sort of laser that's pointing at this nanosphere that's levitating, and then the light that gets backscattered, the light that hits the nanosphere and comes back out the other way, we want to take that voltage or that laser and then do something with the signal and transform it such that it would create some sort of feedback force. So let's say something that's moving, the particle's moving that way. We want to apply a force in the opposite direction to just slow down this particle to its ground state. And this thingy that we're working with will output a voltage that pushes the sphere. And some past research was able to reach a state of 100 microkelvin. Since temperature is related, the thermal motion is related to the temperature. This is really, really cool. Hopefully, I don't want to be in that place. And this is a diagram that I saw that Professor Moore also worked on, where as we reduce, as we slow down, we could get to this state and like basically slow down the motion here. And so the idea of a FPGA is basically this thing that it's a hardware where you can continuously program it after you get it. So I like to think of it as like you get a bunch of Lego blocks and you could build whatever you want. And then if you don't like that design, you could just break it up and build another thing. And what makes it so nice is that it has this parallel processing, so you can run blocks of code at the same time, making it very, very efficient. And so this is the actual repetile that I just kind of sit at my desk and I mess around and look at. And the reason why we use this repetile is that It has a very, very fast 125 megasamples per second. So we could track the motion of this nanosphere that's levitating and do a lot of quick calculations with it. And it also has this FPGA, so it allows us to basically reprogram it however many times we want. And this block design is basically, I basically set my computer and I use Vivado, a program in which I can communicate to the Repetile, make it do what it wants. It's a pretty hefty diagram, so I would say just ignore these because these are just input and outputs. I'll talk more about like the specifics of what each block kind of does. So to start off with like the processing system, this is basically just kind of like the mitochondria of the cell, just kind of like you need it for everything. It does the configuration, the memory, and that kind of stuff. And then there is this advanced extensive interface, the input and output, this one right here, the AXI GPIO. And this basically allows you to communicate with the computer, from the computer to the Repetile. So you can program some sort of software using Python or C, and then you can basically change what the FPGA wants to do. And then there is also this timing clock, which makes sure that everything runs at the same time, especially with 125 megasamples per second. We want all of these little blocks to be working at the same time. And then there is just the ADC converter, where we have some sort of continuous wave that comes in. We want to convert it to digital data that the Repetile could mess with. And then these are the two modules that I've been kind of messing around. So since we have some sort of nanosphere and we get the motion back, we want to be able to scale and shift this data. And also, since we have the position, if we take the derivative, we can find the velocity. And so we know how fast it's moving, and using the scale and the shift, we could basically apply a force that's proportional to the velocity of what it's moving at. And then finally, once we do the calculations, we could convert it back to analog data that would send out a voltage and push the particle. Got it. Thank you so much. And sorry for the lines of code. This is kind of what these little, oops, I didn't mean to do that. What these little blocks have in them, a language called Verilog. And so these are just two kind of blocks of code where we have some sort of, I'll just quickly go over these code because no one likes to read code, but you have some input and some output. So this derivative module, I would take some previous sample, store the previous sample, and then take the difference between the current sample and the previous sample, and that takes you to that gives you the derivative. And then once I've programmed the FPGA, I could use the Linux system on my computer by developing a Python program that allows you to basically talk with the Repetile. So this is what I saw on the on my Linux. So the Repetile is listening on some sort of port through the terminal, and then I developed a Python GUI which allows you to have the user could set some sort of phase and scale it by however much. So if I want to scale up the data, I could basically just tell the Repetile to be like, okay, we have some sort of input. I want it to be 5x larger than what it is. And so since I've been able to, since I could just test this using like a function generated oscilloscope, this blue line is, I give it some sort of input voltage, and then I want to be able to see some sort of output voltage. So this yellow line is some sort of derivative that the Repetile actually changed. And the reason why we want to do something like this is because, like I said, we want to push the nanosphere. So if we could see that we could change the input voltage, this wave, we could apply this wave, this voltage to the nanosphere. And so we could scale it up like this. And as you can see, it's currently not at the best spot, since I would love to keep working on it, where as I scale up the derivative, it gets a bit noisy. And I wanted to plot this somewhere else. I didn't want to take a screenshot of this, but the CSV file was being weird and I couldn't get the noise. So sorry for the oscilloscope pictures. And so some summary, I basically just, the goal for the next few weeks as well is to basically just implement this cold damping feedback in which as the particle is moving, I can push it in the opposite direction to slow down the particle. I also programmed the Repetile's FPGA, use some sort of software, programming a C and Python program that allows you to talk with the Repetile, and then just kind of show results through the oscilloscope. And for the next couple of weeks, I want to be able to implement a full feedback loop. So as this output, as it outputs some sort of signal, I want to use the output as some sort of input, some sort of PID controller, which allows it to basically take out, have something come out and come back in. I'm also maybe changing up derivative approximation that could help reduce the noise. And also this idea of a Kalman filter, which basically combines, predicts what the next steps are and uses the current module to change up the program and basically do the same thing as this feedback loop. And these are some of my references, and thank you so much for listening.
Can you back your oscilloscope slide?
Yes.
Yeah, so on the output, it looks like you have some kind of notch every pi.
Mhm.
Do you know what that is?
The low scale, this one right here?
These little diagonal black lines on your output. So every,
This one?
yeah,
I think that's just noise. I think this is the same blue. So the blue is just connecting the function generator to the oscilloscope. And this is just some sort of noise because the derivative, like this is a very, very zoomed in picture. Because since it's sampling at 125 megasamples per second, this would mean that the frequency is like 1/125 million. So I zoomed in a lot, and I'm guessing this is just probably noise from the original blue line.
I think there's like a sine wave.
Yeah, it's hard to see.
Yeah, and this is a wave.
I see.
Yeah, I wanted to convert to CSV, but like these kind of little things I thought were pretty important. I don't think it's saved through. So
Thank you so much.